Thank you for attending our presentation on reinforcement learning control of a reconfigurable planar cable-driven parallel manipulator. The motivation for this research was to aid in the development of a cable-driven parallel robot for concrete 3D printing. Such a solution is expected to be lightweight, modular, favorable to on-site setup and disassembly, controllable over large workspaces, and of low cost. CDPRs have already been used in a handful of 3D printing applications, although there are no commercially available robots offering this technology yet. The addition of online geometric reconfigurability to CDPRs can offer improvements to the traditional design by making the cable attachment points movable. For example, the additional kinematic redundancy offered by having these mobile cable attachment points can improve the reachability of the workspace, optimize the performance at the end effector, and offer the ability to overcome cable failures through reconfiguration. This is not a new concept. The advantages offered by geometric reconfigurability have been explored in other research, and the challenges of online real-time redundancy resolution control for kinematically redundant parallel robots are well known. Most research in this domain offers solution for dimensionality reduction through clever design modifications or constraints, or by controlling the system in a cascaded manner that does not translate to true online redundancy resolution control. The optimization for all or part of the input state is typically performed offline, and commands sent to the robot in an open loop. This often requires the trajectory to be known in advance and the robot to have no drift. There is one paper that approached it differently, where they turned the optimization into a trained neural network map, but they made an assumption that the boundaries of the cable anchor points don't intersect with the workspace of the robot. So the violation of the wrench closure condition is never really threatened, and one of the major sources of non-convexity in the objective function is removed. These robots are highly nonlinear because their input states depend on each other. There are multiple objectives in the cost function, and even when implemented in a way that offers consistent, locally optimal convex solutions, these functions can be too computationally expensive to be implemented in real time. Deep reinforcement learning can offer an advantage here. In this work, the cable attachment points of the CDPR exist on linear sliders, whose positions form the input state that determines the position and pose quality at the end effector. The remaining inputs are cable tensions, which maintain positive tension and fine directed control. The trained DRL agent acts as a replacement for the controller block. The implemented DRL control attempts to minimize the cable tension without violating the positive tension constraint and simultaneously maximizes the quality of the wrench closure and manipulability. The cost function also rewards trajectory tracking constraints on position and velocity. This was implemented on 3 cases. In the first case, the agent is trained to control only the cable tensions. In the second case, it is trained to control the cable tensions and slider position simultaneously. And in the third case, the training for the tensions and sliders are decoupled. The wrench quality and manipulability in the first case isn't being actively controlled, but is part of the reward function for the second case. We expect to see both these values maximized, but when we compare it with a benchmark ideal result, we see that there is some improvement in the post quality with the addition of redundancy between the first 2 cases, but the cable tension inputs are noisy and not sufficiently minimized. We realized that the agent clearly struggles to train with a non-convex reward function. This is possibly because there is a joint interdependency. The cable tensions change with the change in slider position. So we try to train the 2 input sets separately. By decoupling the agent training, we saw better results. We approached the decoupling in 2 ways. In the first case, by training the slider policy and utilizing the trained agent to train for cable tension. This gave us improved but less than ideal results. In the second case, instead of using the trained agent, we trained for cable tension by using the slider positions that came from the optimization, and we saw significantly improved results. By comparing the results, we see definite improvements with this approach, but the final solution is still noisy and not ideal. Clearly, the DRL achieves the main objective, but struggles to train the non-convex reward function and learns a suboptimal mapping. The chosen TD3 algorithm struggled with multi-constraint reward functions and would often get stuck in local minimas. For example, it would realize that it can achieve a suboptimal mapping by moving a single slider and begin to ignore the potential offered by moving the other 3. The joint dependence made random explorations of the joint space non-compatible. Improvements were noticed through better reward selection and reward shaping, but in future work, we will explore we will explore different algorithms that fit the problem statement better. This concludes our presentation.